closed category, maybe it has coproducts there and 0, then there are various laws that hold. It's kind of the arithmetic of objects in a Cartesian closed category. And indeed, if you specialize to the Cartesian closed category of finite sets, so you just have the numbers 0, 1, 2, and so on, right? Everything's isomorphic to one of the numbers. Then this is just the usual arithmetic of numbers, right? The laws of exponents. There's a distributive law. I should have put that one in too. Oops, use blue. There's the usual distributive law for distribution of products over sums. So all of the usual arithmetic of the natural numbers can be expressed in this setting of Cartesian closed categories. But if you tried to do one of the, and this, by the way, is how I teach my children to do arithmetic. First, I teach them to do Cartesian closed categories, and then I have them try to do these problems the way you tried to do, and you quickly learn that it's very hard to prove these things, right? I don't know, did anyone succeed? Wasn't this a homework exercise, or was it this one? Yeah. Did anyone succeed? Yeah, okay, you got it. So there were a couple of different ways of doing it. One was, so as in the first exercise where you were proving associativity of products, you find some universal mapping property that both of these things have, and then because they both satisfy the same universal mapping property, they must be isomorphic, and then you show that they both have it in virtue of being compound out of binary products in two different ways. So the universal mapping property was just being a ternary product. So if you take a binary one and then associate this way, you get a ternary one, or a binary one over here and associate that way, you get a ternary one. So for these other examples, you could try to do a similar thing and find a compound universal mapping property that both sides satisfy, but there it's more complicated to say what the compound universal mapping property should be. It somehow is assembled out of the universal mapping property for sums and for exponents, and over here out of exponents and products. So that was one way. Another way you could do it, maybe a more kind of logical way, would be to show that the calculus of lambda calculus with sums can be interpreted in a Cartesian closed category with coproducts. That was one of the other exercises. And then you can use that and prove it logically using lambda calculus, do some calculations in the lambda calculus. And then because the interpretation is sound, anything you can calculate will come out to be true, and so you can prove those isomorphisms that way. Now there's a third way to do it. That's the category theorist's way, and it uses some more powerful methods. And that was the point of this exercise, was to get you to appreciate how hard it is to do it with your bare hands, and then how easy it is to do it once you have these more powerful methods. And the more powerful method that I'm going to show you today is called the Yoneda lemma. And once you have the Yoneda lemma working for you, then you've really got some tools. You don't have to do things with your bare hands. So that's what I want to get you to appreciate by doing those problems. And then you'll be able to do all those other problems too in a wink of an eye just by using the Yoneda lemma. So the Yoneda lemma is a fact about natural transformations. So what is a natural transformation? Well, one of the inventors of category theory, Saunders Mac-Lane, famously said, the notion of a category was invented in order to be able to define the notion of a functor. And the notion of a functor was invented in order to be able to define the notion of a natural transformation. And in fact, the first paper on category theory in 1945, Mac-Lane and Eilenberg and Mac-Lane rather, was titled General Theory of Natural Equivalences. So it's this idea of naturality, that the notion of category was invented to get one's hands on, is this idea of naturality. So let's start with a very simple example of a natural transformation. Oh, these are nice pens, thank you. Naturality. Let's suppose we have a Cartesian or a category C, say, with just binary products, just to have something to look at. Then we can always make a product of two objects, A and B, like this. And we can make a product of two objects like this the other way around. And now it's easy to show that these two objects are always going to be isomorphic. So let's just see, what would the map be that goes this way? Well, maps into a product are specified by saying what their two projections are, right? So the projection down to B would just be the second projection from this. So this is going to be the pair pi, did I call them P or pi? P, I think. P2, comma, P1. And similarly coming back. So that's our pair of maps going back and forth. And then you can check by using the universal mapping property of the binary product that that indeed gives you an isomorphism. But now the thing is this. This specification doesn't really depend on the objects A and B. It just depends on this product structure on A and B, right? And that's what we're trying to get our hands on, that idea that we have an isomorphism between these two objects, which doesn't really care about the objects. It only depends on the structure of the objects. So that's the idea of naturality. And this is sometimes called something like parametricity or polymorphism. Maybe you've heard that term. That tends to be the one that polymorphism that comes up in type theory, or uniformity. It's a uniform isomorphism. There are all kinds of terms in the literature. And it's kind of too bad there are all these terms in the literature, because this concept was defined in 1945, and it's called naturality. And I really think the category theoretic conception of naturality, which was invented for exactly this purpose, does exactly what we want. It tells us that this isomorphism is independent of the choice of the objects. It's an isomorphism between these structures. So how does it work? Well, it works like this. We say, let's consider any maps from A into anything else, A prime, and from B into anything else, B prime. So down here we have A prime cross B prime. And here's B prime cross A prime. And now we want to say this isomorphism also exists here. But of course it doesn't make sense, because this isomorphism is between these objects. We want to say there's an analogous one down here. And of course there is one. We can write it in the same way. We get an isomorphism down here. But there's more to it than just that, because how can we specify that this is analogous to this? And that's the issue here, right? How do we say we have an isomorphism here, and it's like that one, but it's different? And right? It's not, you can't say, oh, this is two projections and that's two projections, right? That's kind of using a particular specification. It's using a particular syntactic description. The way that you describe something is not a property of the thing. Okay? You could describe it in terms of the description, but that's not a property of the thing. Here's the way that you do it in an invariant way. You say, consider these maps, F and G. Put them right here. Here's F cross G. Here's G cross F. This diagram commutes. For any pair of maps like this, F and G, you make this isomorphism here, and this diagram will commute. So we have an isomorphism, and moreover, the isomorphism respects any change in the arguments. So that's the idea of naturality. Let's look at the general case, the general definition. So what's really happening is, maybe before I give you the general definition, let's look at it in this special case. This is a functor in two arguments. It's the product functor. And this is another functor in two arguments. It's the twisted product functor. Yeah? It takes the first argument and puts it in the second place. So there's another functor in two arguments, the twisted product functor. And now what we're saying is these two functors are isomorphic as functors. Yeah? So where do these functors go? Well, they go from our category here, C crossed itself, down to C. It takes two arguments, A and B, and it returns, on the one hand, A cross B, and on the other hand, this twisted thing, which is by definition B cross A. And now what I'm saying is I have these two functors, and the functors themselves are isomorphic to each other as functors. So what we need to have is a notion of a morphism of functors. And that's what a natural transformation is. So a natural transformation is, and this is not my definition, this is my description, is an arrow or a morphism. Morphism just means arrow, right? Morphism of functors. Okay. Is a morphism of functors. So we have a category C and another category D and a couple of functors, F and G, from C to D. And now we want to say, what does it mean to have an arrow from this functor to this functor? So we're defining a new concept, a morphism of functors. I'll call it theta here. And now I can give you the formal definition now that I've showed you kind of what type this thing is supposed to have. So definition. Theta between two functors like that, F to G, consists of a family of arrows, family of arrows, theta C from F of C to G of C. So these are arrows over in the codomain here in D, one for each object C and C, such that, so let's look here. I take F of C, I take theta at C, here's G of C, and now let's suppose for any arrow H from C to C prime over in C, I also have here F of C prime, theta of C prime, because I've got one of these thetas for every object in C. And then here's the action of the functor F. Here's the action of the functor G. F of H, sorry. Here's the action of the functor G on H, and I want this diagram to commute. So the idea is it's a way of getting from the functor F over to the functor G, which respects the action of F also on all of the arrows of C. Good? People are nodding their heads. It makes sense, I hope. So I hope you can see that this is an instance of it. Well, this is a natural isomorphism because it's an isomorphism at each step. But if we just look at one direction, for example, then we have a case of this naturality. If we just look at this map that goes across here where it's P2, P1, down here we have a similar twist, P2, P1, twisting this other product, then what we're saying is that twist will respect every pair of maps like that. So that's a natural transformation. Let's see, what else? Do I want to have some examples yet? Question, yes?
Maybe I'm misremembering the definition of functor. I thought a functor went from a category to a category.
Absolutely.
They're going from object to object here.
No. These are the functors right here, F and G.
F and G, and then I'm looking over there and I see FC going to GC with C is an element.
This is an object. C is an object in C.
Right.
I apply F to C and I get an object in D. This little piece of the diagram right here is in the category C.
Right. Okay. So
And then this diagram here, this commutative square, is in the category D. And it's a condition that says for every arrow in C, I get a commutative square like this in D. Is it good? Okay. So let me give you an example. Let's look at the this is the example of sets. Sets changing through time. And of course, you can change all kinds of things through time, not only sets, but so a set through time is the following thing. It's a so so here I'm talking about discrete time. So there are moments of time, 0, 1, 2, 3, 4, and so on. Okay, discrete moments of time. So there's a set at 0, and a moment later, at 1, there's another set A1. And a moment later, there's another set A2, and so on, forever and ever. So this is a set, and it's evolving through time. But of course, you want to know how the elements of the set change as you go through time. So how do you say that? Well, let's say what happens to an element at this time a minute later. What happens to it? So that's a function like this in sets. And here's another function that tells us what happens to the elements a minute later, or a second later, or a moment later. There we go. And so on. So I'm not making any conditions here. I'm not putting any conditions on these functions. So it could happen that two elements that were different here suddenly become the same over here. And it could happen that an element that doesn't exist at all here suddenly pops into existence over here. So that is to say, this function doesn't need to be injective, because things could get collapsed. And this function doesn't need to be surjective, because new things could pop into existence here. But once you have an element, it stays with you somehow. You don't lose it forever. That's to say, these functions are total. They're defined everywhere here. So an element will always have some sort of a trace through time. It won't ever completely disappear. So that's the idea of a set which changes through time. I think it's a perfectly intuitive notion. And we'd like to be able to work with these things, with these sets through time. In particular, we'd like to make a category of sets through time. So one good way of making a category of sets through time, we want to make arrows between them. What should be a function between two sets through time? So here's one, A. That's a set through time. And here's another one, B. So that looks like this. B0, beta 0, B1, beta 1. And so on. So now, what should be a function between such sets? Well, I think a perfectly reasonable thing is that at each stage, at each moment, there's a function from the set at that time to the other set at that time. So for example, here at moment 2, there's a function here, f2. But also back at 1, there was a function here, and so on. So there's a family of functions like that, one at each moment. But if I take some element here and I send it over to in A and I send it over to B, it really shouldn't matter if I send it over to B and then see where it goes, or if I first wait a little bit and then send it over to B. Right? That's just saying that this function is not just an arbitrary collection of functions. It really respects the change through time of the elements. So that's a perfectly natural way, I think, of saying that it's actually a mapping on the sets through time. It's a mapping through time. It preserves this idea of the element changing through time. Well, that's just saying that all of these squares commute, right? It's exactly what it says. Okay, and so that will give us then our notion of a category of sets through time, right? I can compose such ladders. I put another ladder here, and I can take the composites. Then just by reasoning on the diagrams, I can see that the rectangles will also commute if each of the squares commute. So that gives me a composition operation. It'll be associative and so on. So that gives me my category of sets through time. Here's an easier way of describing sets through time. Let's take the natural numbers. Let's write them as omega, because we're thinking of them as ordered. So we have 0, less than or equal to 1, less than or equal to 2, and so on, right? It's a category. It has, these are the arrows. It's a preordered category. In this case, it's a poset category. So these are the arrows, right? And now, the category of sets through time is just the functor category sets to the omega. That is, A and B These are nothing but functors from omega to sets. Let me write it like this because I haven't introduced that notation yet. These are functors from omega as a category into the category of sets. Right? What is a functor from this category into sets? Well, it's an A0, an A1, an A2, together with a family of maps, alpha 0, alpha 1, alpha 2, and so on. So it's exactly that. Right? So A and B are exactly functors. And then this F thing that I wrote down here is exactly a natural transformation from this functor to that functor. That was my definition of a natural transformation. So A and B are functors like this, and F from A to B is a natural transformation. Because a natural transformation in this case is an indexed family of maps, one for each object in omega, so an F0, F1, F2, and so on, such that for any maps in the index category, all the corresponding squares there commute. Good? So the category of sets through time is nothing but the category of functors and natural transformations of the form omega into set. And so now let me introduce this new notation. So the notation is going to be, and notation and terminology is a functor category. From C to D, or the functor category from C to D. D has as objects functors F from C to D, and as arrows natural transformations theta from F to G, and the notation is just D to the C. That's the functor category. So now in that notation, this category of sets through time is what I wrote before. It's sets to the omega. And so here's a fact. I won't prove this, but it's good to mention it now because it justifies our notation. This is, in fact, together with the obvious evaluation, functor, this is an exponential in cat. So that justifies this kind of functional notation. And in fact, cat is Cartesian closed. Cartesian closed category. So that's kind of cool. What it tells us is that we've got the definition of natural transformation right. If we start out asking for a Cartesian closed structure on cat, we know there's only one. If there is one at all, it's unique up to isomorphism, because these things are defined by universal mapping properties. So there's at most one way of making an exponential for any two categories up to isomorphism. And now we ask, is there one? If there is, it determines that functor category uniquely up to isomorphism, and the fact that this holds with that definition of natural transformation tells us we've got the definition right. You can deduce the definition of a natural transformation from this fact. Right? So it's a nice kind of test of that being the right concept. Let me look at some examples maybe. So one way of thinking, it's a little bit hard sometimes to think about these new concepts. It's good just to draw some pictures to get a feeling for it. Here's a picture of a general, in general, a natural transformation looks like this. Picture of theta from F to G. You can think of it like this. So here's the category C, say, right? It has some objects, A, B, C, some arrows between them, composites, some identity or some loops, right? And now we have these two functors over to D, right? A functor is a picture of one category in another category. That's the way to think of a functor, right? It takes all the objects and arrows in one category and gives you an image of them over in the other category, maintaining all the relations of mappability between the objects and even the relations of composition of mappings and so on. So the functor F, which is going like this, gives me a picture of this category over here in this one. So that looks like this: F of A, F of B, F of C, and so on, with this arrows, roughly in the same configuration here. And then the functor G gives me a different picture, perhaps, of the category C over in D. It expresses everything in some other way. But still, it's going to have that same general shape, that kind of CE shape over in D. So it's at least going to have these arrows, and they're going to have to compose in the same way, and so on. A natural transformation consists of a family of maps over in D connecting the image of F with the image of G in a compatible way. So what that means is for each A over here, well, there's a corresponding thing here under F and a corresponding thing here under G. And so the theta gives me an arrow connecting those two. Theta at A. These are called the components of the natural transformation. And for B, there's I should have used I'll use my colored markers here. This is great. Where's that blue one? So we connect the image of those things using the thetas. Theta A, that's better. Theta B, if you like, theta C, in such a way that all the corresponding diagrams commute. It doesn't matter if you start here and go across and go down here, or if you first go down here and then go across by means of theta at C. So that's the idea of a natural transformation. If you think of a good way to think of a functor, I think, is as a kind of construction on the objects here in the category C. So you have these objects and these arrows, and you use them to construct something over in D. I mean, D could be C itself, or it could be some other category, but you have some construction, yeah? Maybe like the simple case was just taking the product of two objects. But it could be a much more complicated thing. It could be a thing that you can't even write down syntactically. But it's some sort of an abstract construction, right? And now G is some other construction. Theta is a way of transforming one of the constructions into the other, right? It's a way of relating the one construction to the other. But it's relating the constructions themselves and not the individual values of the construction. It relates the whole construction F to the whole construction G. And that's our way of describing that idea. Okay, let me give you some very simple examples just to have something more to think about. Remember the category of all arrows in a category? I have some category C, and I make the arrow category. And the objects of the arrow category, which way was I doing this? I want to get this to match up with the way with the orientation that I used there. Okay. The objects of the arrow category are arrows in C, and the arrows in the arrow category between two such objects are commutative squares in C, right? Well, let's let this thing be the category that has two objects and one arrow between them, okay? It's a simple finite category. Well, then we can make the actual functor category from this thing into C, right? What are the objects in the functor category? C to the thing like that, right? So the objects in this functor category are going to look like this. They're going to be things of the form C, one for the dot, one for the arrow, or one for the star. And this arrow has to go to something in C, so it'll be an arrow here. So that'll be one such object. Another such object will be something like this. D, one for the dot, one for the arrow, and then an arrow between them. And then the functor category consists of functors and as arrows, natural transformations. So a natural transformation will be a theta dot, a theta star, such that this thing commutes. So it's exactly this. So the arrow category that we introduced ad hoc is really another example of a functor category where the category in the domain, the functor category, is this simple three-object category. What if we do it, for example, let's take 2. So that thing we're calling maybe, I think when I introduced it I called it 2, like that, it has an arrow. What if I just take 2 to be the category that has these two objects but no arrow between them? And then if I take C to the 2, what do I get? Well, the objects then are just a pair of objects, C, and the arrows are pairs of arrows, but there's no compatibility condition. So that's exactly the same thing as C cross C. So there we have the kind of laws of exponents like over here at work now. How about this one? Let's take as our index category, this is the index category. We did that one, we did that one. Let's do this one. It looks like this. It has two objects and two arrows. Then an object of the functor category, let's do it in sets just to be specific here. What are the objects now in the functor category? Well, that would be a pair of objects, or a pair of sets rather. Let me call them suggestively the edges and the vertices, and two arrows, call them the source and the target. So that's just a graph, right? It's a set of edges, a set of vertices, and each edge has assigned to it a source and a target. And another one would be another such thing. I guess I should use some better notation, but anyway. And now what's a natural transformation between those things? Well, it's a function that takes edges to edges and another one that takes vertices to vertices, respecting sources and targets. So that's exactly a graph homomorphism. Graph homomorphism. So a functor here is a graph, and a natural transformation is a graph homomorphism. So the functor category of sets to the G, where G has this shape, is exactly the usual category of graphs and graph homomorphisms. And in general, you can think of a functor as a kind of into sets, a functor into sets, as a kind of structured set, where the structure is given by the shape of the index category, and a natural transformation between such structured sets is a structure-preserving homomorphism, right? Another example you may have seen is simplicial sets. That's something that comes up in algebraic topology. It's a much more complicated version of this, and then you have a system of sets satisfying some conditions, and then the homomorphisms are the maps. So those are natural transformations. So those are just a few examples. Everybody good? I'm not getting any questions. I guess this must be very clear. All right, let's move on a little bit. Have some time. We're going to look some more at categories of this form, where we have a category up in the exponent, and then we have sets down in the bottom. So these are called, so these are set-valued functor categories. Sometimes these things are called categories of diagrams, also called presheaves. Okay, so these are things of the form category of sets in the codomain, and then some category C up here in the index, either co or contravariantly here. So either co or contravariant functors from C in some small category C into the category of sets. And the basic example that we want to think of is this. Let's remember our Hom functor. Hom was a functor from C up across C into sets. So we're going to assume that C is, we can make it small or what's called locally small. The main thing is that whenever we take two objects, A and B, and we take them across here, and we take the collection of all maps Hom from A into B, that the result is a set. That's the definition of being locally small. Category is locally small if that Hom collection is always a set. So assume that holds so that we have this Hom functor. And we had some exercises before to tell us how to work with that thing. And now this category, this is something happening in cat, right? And cat is Cartesian closed. So we can always, when we have a functor in two arguments into a category, we can transpose it into a functor in one of the arguments, landing into a functor category. So that's what we're going to do. We're going to transpose it like this. We're going to say, take C into the category sets to the C op. Right? We take that op, we put it over here. We're currying this function, or this functor rather. We're currying this functor. So what does it do? It takes an object, say, I was using A for the contravariant argument, so let's use B for the covariant argument. It takes B to the functor Hom blank B. So this is a functor from C op into sets. And if you just think about it for a moment, you'll remember how this thing works. It takes some A here to the set Hom A, B. That's all arrows from A into B. And it takes any map from H into H prime like this. Well, these things are arrows from A into B. So if I've got a map of this shape, I can precompose with it and get an arrow from A prime into B. So that's my action now here. A prime B. The action is by H. I think I called it H upper star. That's just precomposition of some argument with H. So argument after H. And notice the change in direction, and that's why we have this op here, because this is a contravariant functor. Okay?
I missed some of that because you were
Yes?
writing it, so I couldn't see what was going on the board.
Sure.
So I missed the connection between what's on the board and what you said.
Yep. We'll have a look.
You're standing back. Quickly say it again.
I have a functor here. So I have transposed this functor to give me a functor from here into there. Okay? It takes an object B to this representable functor. And the representable functor, right, this Hom functor that we talked about before, and it works like this. It takes an object A in C to the set of all maps from A into B. Okay? And now, how does it act on arrows? Well, it acts like this. If I have an arrow into A, and I have an arrow from A to B, I precompose with this arrow. And that gives me an arrow from A prime into B. Well, so this operation is going that way, where this one's going that way. So that was the definition of being a contravariant functor. And that's why we put this op here, to show that the functor is contravariant. And this is just the definition of the action. It's saying precompose with H. This map here, conventionally denoted Y, is called the Yoneda embedding. And that it is an embedding is a consequence of the Yoneda lemma, which we're going to not completely prove, but at least mention now. The Yoneda embedding, let's see, is that. That's the Yoneda embedding. So here's a fact. We'll just let me just state it, and then we'll analyze it. So I guess what I should say is I know that this thing exists for general reasons. I haven't told you specifically. You have to go and unwind now how this operation acts on arrows and B, right? I showed you how it works for one particular B. How does it work if I change B to B prime? I'll let you work that out for yourself. This worked by pre-composition by A. It works by post-composition with B. That's all. So this just gave me, for each B, it gives me a functor. And now for each arrow here, it gives me a natural transformation over here between those functors. And that's a kind of getting to be a higher level of abstraction here that takes a little getting used to. But that's all it takes. It's just it's one more step of abstraction. It takes a little getting used to. So anytime I have an arrow here, H, from B to B prime, I get over here, it sets to the C up, applying Yoneda, I get YB, a functor, YB prime, another one, and YH. And now this is a map of functors, so it's a natural transformation. So this is living over here. I get a natural transformation between these two representable functors, corresponding to this map between B and B prime. So it's a way of, if you like, representing C as a category of functors and natural transformations. It turns these possibly abstract objects and arrows of C into functors and natural transformations. So it's a more concrete description of this category C. As it's like if you have an abstract group, you can make a representation of it as a group of matrices and with matrix multiplication. This is representing a category as a category of functors and natural transformations between them. So that's what's going on here. And the Yoneda lemma tells us that this is a very good representation. And that's what we're about to see. So the statement for the Yoneda lemma is this: given any C in the category C and any functor F in the functor category, there's an isomorphism of the following form. If I look at natural transformations in the functor category from the representable functor into F, those correspond exactly to elements of the functor F at C. Okay, that takes some getting used to, but it's a nice, beautiful, compact statement. You can put it on a bumper sticker if you like. There it is, the Yoneda lemma. It's probably the most fundamental fact in all of elementary category theory, is that isomorphism. It's a very useful fact. So what it's telling me is this. If I look at, here's my functor, my representable functor YC, and here's my functor F, right? And now these things have values for all objects, right? So let's suppose I have this natural transformation theta going from YC over to F. Well, in particular then, it has values YC at D, or YC at A, YC at B, YC. Where am I putting my parentheses here? Like that. At C, and so on. And for every arrow, A, B, C, down in C, YC gives me arrows like this. And then F2 has FA, FB, FC. Yeah? And now, the Yoneda lemma tells me any natural transformation like this from YC at F is completely determined by one single element living in F of C. One single element over there. So I take my theta here, and it corresponds to something over here, some theta hat, which lives in F at C. What on earth could it be? Well, here's how you get it. You say, look at YC at C. That's a distinguished object here, right? Because the C's match up. And then apply theta. This is theta at A, theta at B, theta at C. So apply theta C to a certain distinguished element in here. What could it be? Well, what is that? That's HOM C, C. Anybody know an object in an element in that set? There's the identity is in there. The identity is in there. So take theta at C. We've got theta for everything, so take it at C, apply it to the identity in here, and you get this kind of universal object over here. It's theta C applied to the identity at C. That's our special object here, theta hat, living in F of C. And now you use the fact that this assignment is natural, and you can basically compute everything about this natural transformation from naturality and this given object. So that's not the proof, but that's a sketch of what goes into the proof. Okay, so now we've proved this thing, but why do we care about this? What on earth does it mean, right? I'll show you how to use it. There's one more little bit there of the Yoneda lemma that I just can't help but put in. I can't bring myself to leave it out. And that is that this isomorphism here is also natural in both arguments C and F. That is, if I change C to some C prime or F to some G, then I'll get a corresponding commutative square involving that change. So there's an isomorphism natural in C and F. It's just a little bit stronger statement, but it's part of the official theory there. Okay, so what does it mean? Yep, go ahead. Yes?
Why did we have on the left side of the home rather than the right side?
Why did what?
Why did we have
Okay, good question, yeah. I'll do it right now. Here's C, and here's this Yoneda embedding, and I want to prove that this is really an embedding. So what does that mean to be an embedding? That's what I'm going to describe now. It takes us from C into here, right? And now the question is, why this? Why C op up here? And the reason is it makes this map covariant. If we had done it the other way around, we'd get a contravariant representation of C. We want a covariant representation of C because the way we think of this whole setup is this. C is some category that we're interested in. We want to do something with it. Okay? This category, which you don't know yet, but you'll soon know, has a great deal of very useful structure in it. This set-valued functor category, it takes the structure that's available in sets and it kind of generalizes it to a category that also involves C. So when I say it has a lot of useful structure, I mean it's Cartesian closed, for example, whereas C doesn't need to be. Sets was, and this thing is too. It's Cartesian closed. It has natural numbers in it as a functor. It has lots of inductively defined types in it. If you're familiar with dependent type theory, it has sigmas and pi's, dependent sums and dependent families. It's a topos, if you know what that is. It has higher order logic. It has an interpretation of all of propositional and all of first order and all of second order and higher order logic. So it has all this logical structure in it. It has cohomology theory, if you know what that is. It has all of this machinery in it, naturally, in a canonical way, living up in this category. Yeah? Whereas this is just any old category. And now, if we knew that this embedding was really good, and we want to study this category, we could go up here, use that machinery to prove things about the objects in C. So we take C and D, we want to prove something about them. We send them up here with the Yoneda embedding, and now we use some higher order machinery up there, right? We use the polymorphic lambda calculus up there to prove something about the images of C and D. For example, we'll prove that there's a map here, just to have something, right? And now what we'd like to know is we can reflect that information back down to C. Even though the methods of proof don't exist down here in C, because C is maybe some very meager category, we can still find a corresponding thing down there. So what we'd like to know is this. We'd like to know if there's any arrow up here between these two things, up in the functor category, then there must be an arrow down here between these two things. I'm just drawing a picture of that home set. Yeah? Moreover, what would be really nice is if we knew that there's a unique one down here that goes to that one. Right? So what's that saying? It's saying the map that takes arrows from here, because it's a functor, any arrow down here goes to one up here. What we'd like to know is that that map is itself a bijection. Right? That anything that is up there gets hit by something down here, and moreover, it gets hit by a unique thing. So that this map from here to here, which is just the Yoneda embedding acting on arrows, is actually an isomorphism, a bijection of home sets. And that's what it means to be, well, and moreover, that it's injective on objects, that it separates objects. And that's what it means for this to be an embedding, and that's true. And it follows in two lines from the Yoneda lemma. There's proof. Let's consider Hom Y, C, Y, D. Well, this has the form Hom Y, C, F for Y, D being F. Yeah? Take F to be Y, C. Apply the Yoneda lemma to get Y, D of C. But what is the definition of Y, D of C? It's Hom C, D. Good? That's exactly what we're trying to show here. Okay. Take F equals Y, D. In the Yoneda lemma. Yoneda lemma says Homming YC into any functor F gives F of C. So for F, put YD and get this. But this is the definition of that. Okay, so this machine that I was describing that we would like to have, we do have. You take any category, you take any objects in the category, you want to prove something about them, but you don't know what to do because your category doesn't have much stuff in it. Well, you apply the Yoneda embedding, you get it up here where you've got all this machinery to work with, right? Calc, everything you want. Right? It's up, yeah, Because it's got like this, it's got the second order lambda calculus is up there. Right? The calculus of inductive constructions has an interpretation up here. You can use calc now to prove stuff about C. And anything that you can prove about these representable functors is true of C and D, as long as it can be expressed back down here. The thing you're trying to prove is some statement that, you know, is about arrows in here. So let me give you some examples now. Yeah.
What is the reverse integral symbol?
That's an isomorphism sign. It's just vertical instead of sideways. Okay. Right, it's this. So my examples, of course, are going to be these things here, because this is what I had in mind when I said you use some machinery rather than using your bare hands to prove these things. So let's prove those things. First, I need to. How are we going to do this? Okay, so do I have? Oh yeah, I have time. Before I do this, let me just remind you of something, and then I'll come back to that. Remember we said last time that the universal mapping properties that define, for example, products or coproducts or exponentials, they're kind of like rules of inference. And I wrote them in that rule of inference style with a horizontal line. Let's just recall how that worked. And then I want to express that in a different way, the same idea, using Hom sets. So for example, for products, we said a product is a thing that looks like this. If you have any x into A and another x into B, well, a pair of maps like that, an F and a G, determine a map from X into the product, which we called FG. And moreover, the universal mapping property says, here, let's write it out right here. We'll say A cross B, B. So this is the way that this works. I say take F, take G, then there exists a unique thing here which I called F comma G, and moreover, this composed with P1 equals F, and this composed with P1 equals G, and this is unique with that property. That was the universal mapping property, right? Universal mapping property. How do you express it as a rule of inference? Well, you say, given these two guys, you can pair them up to get something like this. But moreover, given anything like this, right, some other map here, you can compose it once with P1 to get a map from X to A, and once with P2 to get a map from X to B. So this rule of inference goes both ways, right? You can take something of this form, take its two projections, and get a pair of things like that. So the rule of inference goes both ways. But wait, there's more. Not only does the rule go both ways, but if you compose the two, you get the same thing back out, right? If I start here and I go down, and then I go back up, I get back out the same thing I started with. Yeah? So there's something more going on here than just a two-way rule of inference. It's a bijection between things of this form and things of this form, right? And indeed, if you look at the universal mapping property again from that point of view, it says, if I take things down here, like arbitrary maps here, not necessarily paired up things, I compose with P1 and P2, that gives me a pair of maps like this, right? Then that operation is bijective. Why? Well, because anything in the image, namely a pair of maps, comes from one of these, a unique one, by that operation. So that's exactly saying the operation is a bijection. Anything gets hit, and it gets hit by a unique preimage. Okay, so a third way of expressing this same thing, not to belabor the point, but it's a convenient way of doing it, is this. I look at what's above the line is this. It's the Hom set, Hom XA, Hom XB, isn't it? Well, and it's pairs, so it's that. That's what's above the line. And then there's a map going down to below the line and landing in Hom X A cross B. And how does the map work? It takes F and it takes G and it pairs them up to give me F, G. And now the universal mapping property says exactly that this is a bijection of Hom sets. Good? The map coming back takes some H from X, let me do it this way, some H from X into A cross B, and it composes with P1, P2, to give me the pair of maps P1H, P2H, so that's this map coming back up. Anything of the form H is uniquely of the form pair, blah, blah, blah. Good? So I have this bijection of Hom sets. So let's consider this representable functor here, Hom X blank, from C into sets. Apply to the diagram A cross B, A, B. Apply this functor to that diagram, then you get Hom X A cross B, Hom X A, Hom X B. Well, but these things have a product, namely Hom X A cross Hom X B. So this is exactly this map, right? Let's apply the representable functor like that, and we just said that if this is a product, this is an isomorphism. So this condition says exactly, so the functor Hom X blank from C into set preserves products. So what we're saying is preserves products. It takes a product diagram in C to a product diagram up in sets. And similarly, I want to look at some of the other, I think I don't need this anymore. I can express all the other universal mapping properties that I showed you before like that in terms of Hom sets. And that's a good way to do it because now it's expressed in terms of functors and you can calculate with them. You know, a universal mapping property is a cute way of understanding something because it has this kind of graphical character and you get the idea, but it's not the sort of thing you can calculate with, as you learned by doing those exercises, right? You can't put them together, compose them, get new ones, and so on. So we want to be able to calculate, and this is what these Hom functors are for. So, for example, what was the universal mapping property of the sum? If you think about it, what it says is this. You have the maps into A plus B, B. And now let's think about what happens when you Hom out of this into some other object X, then you get something like this. So what that's telling me is that if I take Hom, and I take A plus B, and I Hom into something else, well then, if I compose on the one hand with I1 and on the other hand with I2, I get a pair of maps, one from A into X, and the other one from B into X. And the universal mapping property again says that that's an isomorphism. So if you like, the contravariant representables, instead of preserving products, they take coproducts to products. And before we already displayed the laws, the universal mapping property for exponentials. We already noticed that that has the form x cross y mapping into b, has such a two-way rule, two-way bijection of x into b cross a, right? We used that last time. That's saying exactly that HOM x cross a, or x cross, a into b is isomorphic to HOM x into b to the a. Okay, so now I've expressed all of those universal mapping properties in terms of isomorphisms of certain HOM sets. And now I can use that together with the Yoneda lemma to do some of these homework exercises. So let's start with, yep.
So with the product, it looks like you define product in terms of product.
In terms of products and sets. I mean, I didn't define it that way, but I'm characterizing it, right, in terms of products and sets. Let's do one, we'll just do number one there. C, we want to show that C A plus B is isomorphic to C to the A cross C to the B. Oh, geez. I need one more fact. Sorry, guys. Let me put my one more fact here that I need. Fact. Any functor like this, which has this property that it has an isomorphism on HOM sets, any functor takes isomorphisms to isomorphisms because isomorphism is defined in terms of composition and identity. So if you have an isomorphism in this HOM set, it goes to an isomorphism up here. Conversely, if the functor itself is an isomorphism on HOM sets and you get an iso up here, well, then this was an iso down here. Why is that? Well, look. So what I'm saying is, if I start with this and I go up here and I get an isomorphism, then there's an isomorphism down here. That's my claim. Okay? So claim, if y of C is isomorphic to y of D, then C is isomorphic to D. I could leave that as a homework exercise, really, but let's just look at how it works. Okay? So the proof is by the Yoneda lemma, and it works like this. You take C and D, send them up here, and get an isomorphism. Well, an isomorphism is what? It's a pair of maps back and forth, and the composite each way is the identity. So the pair of maps back and forth gives me a pair of maps back and forth down here by this isomorphism, right? And now what about the composites? Well, I take the composite of these two, and that's equal to the composite, and then I apply the functor. That gives me the composite up here, right? Well, that one's equal to the identity. The identity is in the image. It's the image of the identity down here, right? But those things now get to be equal up here. And because this is an isomorphism, they must be equal down here. And so the composite down here must be equal to the identity here, because it is up there. Good? Maybe? Is that okay? Yeah, good. Somebody said yes. One person said yes, that's enough. So I'm going to use this fact. Let me put it right there. I'm going to use that fact. If YC is isomorphic to YD, then by Yoneda, C is isomorphic to D. And now I can do some of these homework problems. Where should I do them? I'll do it right here. I don't deny that it's a bit much theory the first time you see it, but hey, nothing's free, you know. The question is not, is it a lot, but is it worth it? And so that's what I want to persuade you of that it's worth the trouble, because once you've built the machine, it works. So I want to show that c to the a plus b is isomorphic to c to the a cross c to the b. But of course, I'll use the Yoneda principle now, and I'll show instead that y of c to the a plus b is isomorphic to y of c to the a cross c to the b. Well, what's this? This is hom blank c to the a plus b. And this thing, which it's supposed to be isomorphic to, is hom blank c to the a cross c to the b. So that's what I'm trying to show. So let's give it an argument. Well, this, we know, is hom x cross, oh, I should have done it in the other order, shoot, because I need that first, c. I should have done that one first, sorry. Give me this one, I'll show you that one in a minute, okay? And because I'm going to use it right now. So now I distribute this in. And now I use that fact about coproducts that I can pull them out on the left of a Hom set. I can pull a coproduct out on the left of a Hom set. I already showed you before that I can pull a product out on the right of a Hom set. Hom x a cross b. I showed you that before. Hom, just to record these rules. X a b. That's the rule for products says you can pull a product out on the right in a Hom set. The rule for coproducts says you can pull it out on the left in a Hom set. The rule for exponents says you can transpose up. Okay, so pull this one out. Now what should I do? Well, I can put the exponents back up. And now I can use the rule for products on the right. That's it. It's still true. You get the idea? You can reduce these things now to very simple calculations. Yep? Yes. Sure. In a sense, but only in a sense, because give me a locally small category that's not locally small somewhere else. I mean, that's a question of foundations, right? It's a question of foundations. So it depends on how you're defining your concepts. But yes. I mean, locally small is not much of a restriction, right? Every category you know is locally small. Mm-hmm.
Why do sets play such an important role here? It comes from the fact that home are sets.
Yeah. So if we don't need this to be sets. We could do it over any other category that has enough equipment to define the notion of a category or locally small category. We could do it into a background type theory or a background category of a Grothendieck topos or a category of topological spaces. It's really a question of where that Hom lives. And in the elementary case, we start out by thinking of the Hom as being a set and living in sets. But again, that's a kind of question of foundations. So it's kind of a relative thing. Should I do one more? Yeah, I have a minute. Let's do one more because then I will cash this check. I'll do that one. So I want to show that A cross B plus C is isomorphic to A cross B plus. So it's the distributive law, right? A cross C. So in fact, in any Cartesian closed category with sums, products distribute over coproducts. It doesn't have anything to do with the exponents, right? We said that we're looking at distributivity of products over sums. If we know that there are exponents around in the Cartesian closed category, it forces the products to be distributive over the sums. That's kind of funny, isn't it? That actually is a special case of a more general fact that we'll meet in the next lecture. It's because this operation of taking product with A is a left adjoint. The exponent in a Cartesian closed category, it has a right adjoint. So this operation is left adjoint to this one. And adjointness is exactly this, that maps out of this one correspond to maps into that one. And now it's a general fact that left adjoints preserve coproducts. So this is saying that this left adjoint preserves the coproduct. And that's how I teach my kids the distributive law for arithmetic. So first we learn that left adjoints preserve coproducts. Okay, so we want to show that. So we have to show, we'll use Yoneda, so we have to show that halming into this thing, should I halm into it or should I halm out of it? Let's halm out of it. So we'll use the same argument, but we'll dualize everything. We use the theory of duality, right? We do everything over C op rather than C, and we halm out of this thing. So we halm A cross B. Remember, I told you that this principle of duality is a pretty slick business. So here I'm using it, and I don't really have to think much about it. I can just do it formally. In fact, all of these calculations are purely formal now that I've built the machine. So that's what I'm trying to show. And I'm halming out of that. And I need to show that I can get this isomorphism. But this thing now I know is halm B plus C x to the A. And now I pull the coproduct out on the left. And now, let's see, do I just put them back down? Yeah, I just put them back down. A cross B x, yeah, that's it. And now I can push the coproduct back in on the left. So, there we go.
Second step, on the derivation on the left, are you using this back?
This one?
Second step.
Right here.
Or, yes, is it?
Right here.
Yes.
Yeah, you didn't hear me say that?
Oh, sorry, yeah, I messed up.
Yeah. I said here, I said, oops, I did the exercises in the wrong order. I should have done that one first and then this one. So I said, give me this for now, and I'll complete it, and then I'll owe it to you. So that's what I did right here, and now I just cashed the check. Okay, so there's something else that I wanted to say, but of course I don't have time to say it, but I'll just mention it, and then I'll say it next time. And that is, it's good to know that this Yoneda embedding has some if the category C is known to have some structure that you're interested in, it's good to know that the Yoneda embedding preserves it. So, for example, if C has finite products, then the Yoneda embedding of C cross D, well, what's that? That's halm blank C cross D, but we just checked that that's halm blank C cross halm blank D. Right? That was one of our rules. It's this one. The products pull out on the right. So that tells me that the Yoneda embedding itself preserves products. So I have to talk about this a little bit next time, but the Yoneda embedding preserves products. Moreover, if this is known to be Cartesian closed, the Yoneda embedding preserves exponentials as well. It preserves all the Cartesian closed structure that exists down here. So if this is a Cartesian closed category, then this functor preserves all the Cartesian closed structure up to here. I haven't shown you yet that this thing is Cartesian closed. I'll do that next time too, okay? And that this preserves it. But what that tells us is that we then have a model of any lambda theory that's modeled in this Cartesian closed category gets a model up here which satisfies all the same sentences in the lambda calculus, that is, all the same equations of lambda terms, and habitation conditions on types that are satisfied down here. And from that, we can infer a completeness theorem for the simply typed lambda calculus with respect to these very special models of this presheaf form. But we'll do that next time. Thanks.